introduction about Gauss's law applied to spherically symmetric charges. I'm going to consider two cases. One is an isolated point charge, positive, Q, and the other one is that same positive Q but surrounded by a neutral metal shell. Okay, so what is Gauss's law? Gauss's law allows you to determine the electric field at a given distance from the center of the spherically symmetric distribution. And it's very, very simple. Gauss's law, all it requires is that you determine how much charge is inside of a given value of little r. So for the point charge, here's your little Gaussian dude. I just gave him a red face. And the question he always asks is, how much charge is inside of this point where I am? I'm a distance r from the center being right where the charge is. And in this case, of course, the answer is plus q, right? So in this case, all you have to do to determine the field at any distance r, it's a variable, from where the charge is, the source charge plus q, is put in that value of q in. So you get this simple expression, kq over r squared. And if we plot that as a function, we just get that beautiful 1 over r squared decreasing thing, right? So our function there is that. And if I draw a little electric field vector out here somewhere, I'll do it right here on the Gaussian surface. By the way, this dashed thing is called the Gaussian surface. And that's where the Gaussian dude is. He's right at that distance r from the origin. So, for example, the electric field down here below the Gaussian dude would point away. And so if you like, ER, the vector, is the radial component with a subscript r times r hat, where r hat is just a unit vector pointing away from the origin like that. So that's as simple as it gets. That's the isolated point charge. And that's all there is inside of the dude. And so kq over r squared is the field that you observe, as you guys know. Okay, applying the same idea to the same situation, except now surrounding plus q with a neutral metal shell. What changes? Well, the fields are still there in the first region, right? When we're in the first region, little r less than a, you can imagine little Gaussian dude, there he is, right? And he asks the same old question, right? How much charge is inside of where I am right now? So where is he? Well, he's a distance little r away, and little r is now less than a, right? So this is my Gaussian surface, and that's where the little guy stands. What does he see inside of him? Well, just q, positive q, right? So q in is positive q, so that means ER in that region, what I've called region 1, is equal to kq over r squared. So nothing has changed. Inside of the space enclosed by the metal shell, the field is just as it was before. It just looks like the field due to a point charge, falling off like 1 over r squared. Let's plot that down here. At the inner surface of the shell, this is the inner surface of the shell, what do you get? Well, you get kq divided by that particular radius squared. So that's our function. That's in region 1, right? This is region 1. Region 2, well, this is a static equilibrium situation. So region 2 is inside the metal. And when you're inside of metal, free electrons fall. And so the effect of that is that the electric field inside, that is for our variable little r between the inner radius A and the outer radius B, is just 0. And all you have to say is metal, right, or inside metal, and you're done. What about outside? Outside, we put a little Gaussian dude outside. Here's my little Gaussian dude. And he's sitting on a Gaussian surface, spherical Gaussian surface. Now my little r is now greater than the outer diameter. Here's my little r now. I'm in that third region, outside of the shell. And he asks the same old question, right? What's qn equal to? Well, in this problem, I stated that the shell was neutral. What that means is the charge charge on the inside plus the charge on the outside equals 0. So I know that the only charge he sees outside is equal to Q. So outside, that means that the Q in is Q, so I just go KQ over R squared. So that's going to be the field outside. And that is as simple as that. But how do we achieve zero field inside? Well, we got to stop the field in region 1. And in this case, it's all about having charges on the inner and outer surfaces of that shell. Basically, what's happening here is that the positive charge Q is polarizing that shell. And to stop the field, let's go to region 2. Right? In region 2, the only way to get this zero field is, I'm going to put my Gaussian dude in. Let me make him green, just so you can see him, because there's too many Gaussian dudes here. There's my little green Gaussian dude, and that Gaussian dude is now inside of the metal shell. For the field to be 0, that means you must have Qn equal to 0 at that location. There's only one way to do that, and that's to put some charge on the inner surface, that is at little r equals A. Let me show you with symbols here. To stop that field, I've got to put negative charges on that inner surface, right? But the Gaussian dude is very specific. The Gaussian dude, let me put it back in green, the Gaussian dude says, inside a metal, says one thing. He says Qn equals 0. But Qn, in this case, is equal to plus Q, which is just that point charge at the origin, plus the charge at R equals A, right? And this has to be 0, because that's what metal does. So that means this has to be negative Q, right? But if the charge at R equals A is negative Q, there has to be an equal and opposite charge on the outside, because in this problem, it's given that my metal shell is neutral, right? So I can say that on this surface, I must have, that is Q at R equals B, the outer surface, I must have a positive charge so that the shell is neutral. Okay, let's plot this. On the inside, it's 0. But let me keep track of the fact of where the charges are, right? At the origin, we've got our plus Q. Here, we have to have a minus Q to make the field inside of the shell 0. But our shell is neutral, so on the outside of the shell, you have to have an equal and opposite charge, right? These two add to 0 because it's a neutral shell. So what do things look like outside? Well, outside, you just have KQ over R squared, so we can plot that at little r equals B. This is at the outer surface of our shell. You're simply going to have a field equal to KQ over B squared. Here, let me clean that up a bit because this is getting in the way. So that is, and that's B squared. Because that's where we are, right? We're at little r equals B, so we put in, for little r, we put B. And then it just dies off, right? In that smooth way. So this function here is still KQ over R squared. So that's about as simple as it gets. Now I'm going to do another recording on quiz 1. I hope that introduction helps.